up with the length of the messages, so this is looking good to me. Let's review the difference between the length and the capacity of a slice. Sometimes this can be a little bit confusing. The length is the thing that you're going to care about most often. The length just tells you how many things are in that slice, right? If I have 5 items, then the length of the slice is going to be 5. The capacity of a slice reports the maximum length the slice can assume, right? Before it gets kind of reassigned into a new array. So capacity is really, again, only something you're going to care about if you're worried about performance, but the length you'll be concerned about just for kind of normal business logic reasons, right? Just because you want to know how many things are stored in your slice. So to answer this question, it says, what does the cap function return? Answers are the last element of a slice or the maximum length the slice before reallocation of the underlying array is necessary. And the answer is going to be the maximum length. The next question is, what does the length function return? Current length of the slice or the maximum length of the slice before the reallocation is necessary? And the answer is going to be the current length of the slice. And we haven't really talked about this yet, but I'll just kind of inform you as we answer this question. It says, what do length and cap, the two functions, do when a slice is nil? Do they panic or return 0? And the answer is that they return 0. They are safe functions to call. They won't make your code panic and error and crash, right? I don't know how much we've talked about panicking up to this point in the course, but panicking just means runtime error that's unrecoverable. Generally speaking, you don't want your code panicking, and you want to write your code in such a way that it can't panic. So again, length and cap here are safe. They will never panic if a slice happens to be the 0 value, which is nil. Time for some variadic functions. This sounds like a really complex thing, but we've actually been using variadic functions up to this point in the course because the sprintf, printf, printline, all of those functions are actually variadic. So a variadic function receives the variadic arguments as a slice. Let's take a look at the syntax. So here we have a sum function, and its function signature is just maybe a little bit different than you're used to. Basically, we have this nums parameter, which is of type ... int. Now, here's the thing. ... int, as far as the function definition is concerned, is just a slice. We treat this just like we would if it said, square brackets int. It's just a slice of integers. So you're probably sitting there thinking, well, why can't I just use a slice of integers? Why can't we just keep it simple? Why do we have to do everything differently? Okay, well, don't worry too much. The difference is on the caller's side. So the function definition is the same, whether you use ... int or square brackets int. But if you use a variadic function, then the calling code, so the code that uses the sum function, can actually pass in kind of any number of arguments, and they'll come into the function as a slice of integers. So here we could call, for example, sum 1, 2, 3, and the sum function gets a slice of integers with, the values 1, 2, and 3 in the first 3 indexes of the slice. This means that the caller could also call sum 1, 2, right? And we'd have a slice of length 2. So it kind of just gives the caller of the function a different syntax, and specifically kind of a more flexible syntax for how they're able to pass in sort of a dynamic number of arguments into the function. Now, again, we've already been using variadic functions. You probably remember the print line function, right? This is how we print text to the console. It's a variadic function, ... interface, right? So it can take any number of arbitrary inputs and it sort of prints them all out with new lines in between each element. Now, along with variadic function definitions, we also have another operator called the spread operator. And the spread operator is kind of like the inverse of a variadic function. By using the spread operator, we're able to take a slice of values and pass them into a variadic function. So this isn't the intended use case 100% of the time. Otherwise, you just define your function to take a slice of strings and you'd pass in a slice of strings. But if you do have a function that is already variadic and you want to pass in a slice as the variable part, then you can use this spread operator, this trailing ... to sort of spread out, in this case, this name slice into the variadic function. Let's get our hands dirty with this. So it says we need to sum up the costs of all individual messages so that we can send an end of month bill to our customers. Complete the sum function so that it returns the sum of all of its inputs. Cool. So this is going to be very similar to this sum function, right? The difference here is that we're using float 64s and we're going to write it from scratch so that we get our own crack at it. Okay, so first things first, let's create kind of the default sum, which is going to be 0.0.0. So let's say total. Now remember, we can treat nums as just another slice of float 64s. So for I : equals 0, I is less than length of nums, I plus plus, total plus equals nums at I, right? Return total. Cool, pretty straightforward. Let's go ahead and run that. So summing 3 costs, bill for the month, $6, 5 costs, 15, 10 costs, 55. Do these match up? Looks like, yep, that should be 6. 6 plus 4 plus 5, that's 6 plus 9, that's 15. Yep, this is looking good. I'm gonna go ahead and submit that. Now, I told you that resizing slices is possible. We just haven't really done it yet. That's what the append function is for. So the built-in append function is actually a variadic function, but it allows us to just add new things to the end of a slice, and it automatically takes care of adjusting the length and the capacity of the slice accordingly, right? Allocating new underlying arrays as necessary. Now, here are your syntax options for using the append function. If you just want to append one thing, then you'll use this top option. Let's say we have a slice called slice. We want to append a variable called one thing to it. Basically, we call the append function, we pass in the slice we want to append to as the first item, we pass the variable that we want to append onto the end as the next thing, and then we reassign back into that same slice. Now, because append is a variadic function, we can append multiple things, right? So if we want to append the first thing and then the second thing after that, we could do it like this. And obviously we could also use the spread operator if we want to. To be 100% honest though, 99% of the time you'll be using this first one because you'll just be appending items one at a time. Let's hop into the assignment. It says we've been asked to bucket costs for an entire month into the costs that occurred on each day of the month. So complete the get costs by day function. It's to return a slice of float 64s where each element is the total cost for that day. Okay, so we have like this giant list of costs and we need to kind of condense all the costs that happened on a specific day into one index for that day. Makes sense to me. The length of the slice should be equal to the number of days represented in the costs slice, including any days that have no costs up to the last day represented in the slice. Okay, cool. So if we have costs just for, say, the first month or the first day of the month and the 5th day of the month, then we should have kind of 5 indexes in our resulting array with kind of a non-zero value in the first and the 5th indexes, zeros in the middle, and nothing after that. Okay, here we've got an example. Given this input, so day cost, so we have costs on days 0, 1, and 5. This would be the resulting array, right? $4 on the first day, 5.2 on the second day, because we sum those, right? And then on that last day, we'd have 2.5. Cool, let's write the function. So first things first, we're going to need a slice to append into. So costs by day, we'll make a new slice of float 64. And here I'm just using the slice literal syntax instead of the make function. They're pretty dang similar. Now we're probably going to want to iterate over all of the costs. So for I colon equals 0, I is less than length of costs, I plus plus. Costs at I. Okay, so a cost is this structure here, and we can take a look at the day there. We're going to need to figure out basically when we're appending to this costs by day slice and when we're just adding to an existing index. So I think the easiest thing to do would basically be to say if day is greater than the length of costs by day, actually it's going to be a 4. So like while the day is greater than the length of cost by day, we're going to append cost by day equals append cost by day 0.0. Right? So in effect, this for loop here just says if I've encountered a day that I don't yet have room for, I'm going to grow the slice by just appending zeros until I have enough room. So once we're done with that loop, we should be able to assign directly into the costs by day by basically saying cost by day plus equals cost.value, right? Because it starts at 0. So then we can just add the cost. And again, if the day is less than cost by day, then we just don't do this step. We just skip over this for loop. So that's looking correct to me. I'm going to go ahead and return costs by day. And let's run that code. See what we get. Undefined day. What did I screw up here? Yeah, needs to be cost.day, right? Access that field. Invalid operation. Cost by day plus equals cost.value. So cost.value is a float 64. Costs by day is a slice of float 64s. Right, because this is a slice. So costs by day at cost.day. Right? Right, because the slice that we're returning, the indexes in each, or the indexes of the slice represent each day in the month. So we need to index back into the day. Okay, try that. Whoa, what do we got? Panic, runtime error, index out of range, 0 with length 0. Okay. What did we screw up? So, somewhere we are indexing into a slice where the value doesn't, like the index that we're indexing with is outside the range of the slice. So we haven't really talked about this. This is probably great that we ran into this bug. If you try to index, which is this operation here, so like this is indexing into index 5, right? But here we're indexing into cost.day, which holds an integer. If you try to index into an index that is outside the length of the slice, so you have a slice of length, say 3, and you try to access index 6, then you'll encounter this error. That's what we're seeing here. So it looks like that's what we are doing. So for cost.day is greater than the length. Now let's think about that. If the day is 5 and the length is 5, we're not going to do our growth. So I think I have an off by 1 error here, right? What I actually want to do is say if the cost.day is greater than or equal to the length, right? Because an array or a slice of length 4 actually only has 3 kind of indexes. I mean, it has 4 indexes, but they start at 0. So like length 4, the indexes are 0, 1, 2, and 3, right? Let's go ahead and run that again. Cool. No more panic. Day 1, $1, or day 0, $1, day 1, $5.10, day 2, $2.50. Let's see if that lines up with the test suite. So here it looks like day 0 should have 1. Day 1 should have, 5.1 if we add those together. And day 3 should have 6.3? Yep, 6.3. Okay, this is looking correct to me. Slices can hold other slices, right? This kind of creates a 2D matrix of values, right? So for example, here, a 10 by 10 matrix of integers would look something like this, where the first slice is just a slice of slices. Hopefully that makes some amount of sense. If not, don't worry, we'll get into the assignment here in just a second. So it says, we support various graphs and dashboards on Textio to display message analytics for our users. The UI for our graphs and charts is built on top of a grid system. Let's build that grid logic. So this is super common in graphics development, right? We're kind of building on 2D screens, so we need sort of an X and a Y cell within a matrix, which is, again, often represented as a slice of slices. The assignment says, complete the create matrix function. It takes a number of rows and columns and returns a 2D slice of integers where the value of each cell is I times j, where I and j are the indexes of the row and column respectively. Okay, cool. So create matrix, we get 2 integers representing how big we want the matrix to be, and we just have to return the matrix. Okay, cool. So let's go ahead and start building that out. First, we need to create or initialize the matrix. So let's say matrix, slice, let's use make, slice, int, right? And we can just initialize it to a length of 0. It doesn't matter, we're going to grow it. And for I : = 0, I is less than length of rows, I++. And then we're going to need an inner for loop, manage j, which is going to deal with the number of columns, j++. Okay, so what do we do when we get to the first row? Well, the first thing we need to do is make a new slice to represent the row. So we'll say row, make, and we can just do a single slice of integers. Again, row length of 0 is fine. We could pre-allocate, but it probably doesn't matter too much at this point. And then for each j, we're now going to append into the row. So we do row equals append row I times j, I believe was the formula, right? We want every cell to be the result of I times j. So the values will sort of grow out as the matrix gets larger and larger. Cool, so that's adding this inner loop is adding values to each individual row, and then we just need to append the row to the matrix. So matrix equals append matrix row. And then when we're done appending all of the rows to the matrix, we can return the matrix itself. Go ahead and run that. Invalid argument, rows, variable of type int for length. Let's see what we got here. Where did I screw up this time? Right. I don't know why I'm checking a length here. Rows is just an integer. It's not a slice with a size. Let's try that again. Cool, creating a 3 by 3 matrix. Does that math check out? 1 times 1 is 1, 1 times 2 is 2, 2 times 2 is 4. Yep, that looks good. Cool, let's submit it. I want to show you a common pitfall that you might fall into when dealing with slices and how you can just outright avoid it. This is something you should pretty much never do. When you want to append to other slice, in this case, you want to append elements to other slice, you should always reassign into the same slice. So this should read other slice equals append other slice element. You don't want to be appending kind of into one thing and reassigning into a separate slice. You'll run into some bugs, and we're going to talk about how that works right now. So in this first example, we have these slices A, B, and C. And by the way, I would highly recommend coming here on boot dev so that you can actually kind of look and puzzle through what's going on in the code rather than just seeing it on the screen. But basically we have these slices, and when we append to them, we're breaking the rule, basically. We're appending, for example, here 4 onto A, but then returning the value returned by append, we're kind of saving it into a new slice called B, which again, you generally should not do. You should just save it back into the same slice, A. But anyways, we're going along kind of doing that pattern. And at the end, you'll notice that nothing too terrible happened. Basically, we ended up with an A with 3 zeros, B had 4 appended to it properly, and C had 5 appended to it properly. So you could kind of take away from this example, well, maybe there's nothing wrong. Maybe we can just kind of break the rule and append into new slices. Seems like everything's working like I'd expect. And it's worth pointing out that we can even print out the addresses in memory of the slices B and C and see that the addresses are different. In other words, when we called this append functions where we append 5 onto the slice A and save it back into the variable C, we can see that actually C is being kind of copied into a new location. So again, everything's kind of working as we'd expect. Now, it's really in this example 2 that something very strange happens. If we look down, here we're appending onto J the value 4, and then we're appending onto G here the value 5. But the interesting thing is that after we append 5 to G, if we print out J again, we can see that J was actually changed kind of under the hood, right? Up here, J had 4 in its 4th index, and then we never touched J again directly, but by appending onto G, we actually screwed up J. We mutated J. And the reason for that is because in this example, because of the way we've sloppily used the append function, G and J actually point to the same address in memory. So mutating G changed J. Now, I already mentioned that we were doing the same thing up here, right? We were using the same kind of sloppy use of the append function that I'm recommending to avoid, but we only had the bug in example 2. And the reason for that is because the original slice in example 2 has a capacity of 8, while the original slice in example 1 had a capacity of 3. So what that means is when we used the append function in the first example, once we went over the capacity, we allocated a new underlying array, which is why we got different memory addresses. And so when we mutate C here, C is in a different place in memory than B, so they're kind of operating independently, which is, again, what you usually want in your code. However, because the capacity was already large enough in example 2, there was no need for the append function to create a new underlying array. So G and J point to the same array in memory. Again, which means if we mutate G under the hood, we're just mutating J. So again, the way you can avoid all of this headache is to just not do this, right? Append onto the same slice pretty much every time, unless you have like some crazy specific reason not to do so, which like I'm skeptical that exists. I certainly haven't run into it in, many years of writing application code in Go. So the question for this quiz is, why is 5 the final value in the last index of array J, right? So why did we have a 5 here? even though we appended 4. And the answers are J and G point to the same underlying array. So G's append over row J. The Go team is trolling. I think that's obviously not it. And because append only works properly when the number of elements is less than 10, that would be very silly. So it's definitely this middle one. We're overwriting the same location in memory. Next question on the same topic is, why doesn't the bug regarding slices J and G in example 2 occur in example 1 as well? And the answers are because there are fewer elements and Go's runtime can't handle more than 8 elements. That would be awful. Or the array's cap is exceeded, so a new underlying array is allocated, and that one is the answer. So the next question is, how can you best avoid these types of bugs? Don't use the append function, always assign the result of the append function back into the same slice, or always assign the result of the append function to a new slice. Well, it's not using a new slice. That's how we got into this trouble in the first place, and we definitely want to use the append function. It's pretty useful. So again, always assign the result of the append function back into the same slice. You'll avoid a lot of headache that way. Finally, some syntactic sugar to help us iterate over the elements of a slice. You've probably been wondering for the majority of this chapter, do I have to do this like I equals 0, I is less than the length, every time I want to iterate over the elements of a slice? Other languages have syntactic sugar to make it easier, so does Go. So the syntax is pretty simple. This is it right here. And basically by writing it this way, index at each iteration of the loop will be equal to the index in the loop, starting at 0, right? So 0, 1, 2, 3, and then element is the value associated with that index, right? And then obviously slice here is the name of the slice. So range is really the interesting keyword that allows us to iterate over everything stored in a slice. To give a more concrete example, here we have a slice of strings called fruits, and we can range over the fruits. And if we print I and fruit in this example, then we print 0 apple, 1 banana, 2 grape, and so on. Let's jump into the assignment. It says we need to be able to quickly detect bad words in the messages that our system sends. Complete the index of first bad word function. Okay, so that's this. It finds any bad words in the message. If it finds any bad words in the message, it should return the index of the first bad word in the message slice. This will help us filter out naughty words from our messaging system. If no bad words are found, we'll return -1 instead. Use the range keyword. Okay, cool. So the bad words themselves are defined for us and passed into our function. And then the message itself is already broken up into words, it looks like, and passed in as an array of strings, right? So I'm kind of just figuring this out by looking down here. So we have a slice of bad words and a slice of words in the message. Hey there, John. Okay, cool. So let's start by iterating over all of the words in the message, right? Seems like a reasonable place to start. So for I word := range message. And then we want to check and see if one of these words is equal to one of the bad words. So we're going to use a nested loop, actually. We'll do J bad word in range bad words, right? And then here we can say if word = bad word. That means we've found the bad word and we can return, we want to return the index, so we return I, right? That would be the index of the bad word. Otherwise, if we don't find a bad word, we'll just keep going. In fact, we'll just keep going through all the bad words and then we'll keep going through all the rest of the words. And if we get to the end of everything without finding any matches, then we can just return -1. Makes sense, right? Cool, let's run that. J declared not used. Right. So we've come across this syntax before. We can ignore variables with an underscore, right? Let's run that. Let's take a look at our test suite. Scanning message, hey there, John, for bad words. Index -1. That means none were found, right? Which makes sense, we didn't have any. Scanning message, oh my, frick, for bad words. Frick is a bad word. Index 3. Okay, this is looking good to me. I'm going to go ahead and submit that. If you're familiar with object literals in JavaScript or Python dictionaries, then maps in Go are essentially the same thing. Maps are just a way to associate a key with a value. So let's take a look at this example. We create a new map with this syntax here. We're going to use this built-in make function and then pass in the type of the map. So map of string to integer. So we're mapping strings to integers. And we're going to say inside of the ages map, we're going to set the key John to the integer 37. So again, we're mapping that name John to the value 37. Rather than creating an empty map and then kind of adding key value pairs one at a time, we can also declare the entire map up front and use kind of this colon syntax to separate the keys and the values. And then we can also check how many keys, I guess keys and values, are in the map by using the built-in length function, similarly to how you would use it on a slice. So in this case, we create a new map, we create 2 keys, each with their associated values, and then by printing the length, we'll just print the number 2. So let's jump right into the assignment. That's usually the best way to get an idea for how all this syntax works. Assignment says we can speed up our contact info lookups by using a map. Looking up a value in a map by its key is much faster than searching through a slice. So when we look up something in a map by a given key, that's going to be an instant lookup. If we had stored it in a slice, then we'd have to search through the entire slice, sort of index by index, looking for the value that we want. So maps can be a great way to make our code more efficient. The assignment says complete the getUserMap function. It takes a slice of names and a slice of phone numbers and returns a map of name to user structs and potentially an error. Okay, so let me expand our coding window here. Okay, so we're returning a map of string to user structs. Looks like the user struct is defined right here. If the length of names and phone numbers is not equal, return error with string invalid sizes. The first name in the name slice matches the first number, and so on. Okay, cool. So first things first, we're gonna have to create a new map. So we'll do user map colon equals, and I'm just gonna create a literal, a new map literal. Actually, no, I won't. I'll use the syntax from up here. This works just fine. So we'll use the make function. So make map of string to user. All right, so that's now an empty map. And then what we're going to do is check and make sure that these are the same length. So if the length of names does not equal the length of phone numbers, then we'll return nil. So nil is the 0 value of a map. We could also return an empty map of the same type, but I'd say you should prefer nil for slices and maps and things. And then the error should say invalid sizes. So errors.new invalid sizes. We'll import the errors package. Okay, cool. So if we get down to line 13 now, we should know that both of these slices, names and phone numbers, are of the same size, which means we can loop like this. So for I starting at 0, I is less than the length of, it doesn't matter because they'll be the same, right? Length of names, I plus plus. Then we can say name is names at I. And we can say phone number, phone numbers at I. Okay. And then we're going to want to insert values into the user map. So we'll do user map at the key. In this case, the key is the name, right? So key is the name. And we'll set it equal to a new instance of a user struct, so user. And the user struct has 2 fields, name, which will just, again, be the name, and the phone number, which will just be this phone number here. Cool. So that should fill the entire user map with all of the names and phone numbers. And then by the end, we should just be able to return user map nil. Okay, cool. I think we got everything. Let's go ahead and run that and see what we get. So creating map, key, John, value, name, number, key, Bob, value, name, number. This is looking this is looking correct to me. Here we have creating a map with invalid sizes. If we take a look at the tests, yep, that makes sense. The second test has 2 names, but 3 numbers. So I would expect it to get that invalid sizes error. Cool, let's submit that. So the primary way you interact with maps is just by setting and deleting values at a given key, right? They're very associative, right? A value maps to a key, but there's no other ordering. Maps aren't ordered from, index 0, 1, 2, 3, like a slice is. Everything's unordered. You're literally just mapping values to keys. Okay, cool. So let's take a look at some of the different syntax that we can use to interact with maps. So we can insert an element by just setting the key equal to the value. We can get an element out just by accessing it directly at its key. We can delete elements by using the built-in delete function, where we're passing in the map itself and the key that we want to delete. Notice that we're not passing in the value at all. We're just passing in the key. And then we can also check if a key exists by parsing the return value of kind of this access syntax into 2 separate values, where the first value will be the element itself, and the second value is a Boolean. If the Boolean is true, then the element will be whatever element was stored at that key. However, if the Boolean is false, that tells you that that key didn't exist in the map, and the element will just be the 0 value for its type. Let's jump into the assignment. So it says, in fact, let me resize this a bit. It says it's important to keep up with privacy regulations and to respect our users' data. We need a function that will delete user records. Okay, complete the delete if necessary function. It takes a map of users and a name, which I'm going to guess is the key in the map, and it will return a Boolean saying whether or not the user was deleted, and then an error if something went wrong. Okay, cool. So if the user does not exist in the map, return the error not found. Oh, interesting. So if we're trying to delete something and it's not there, that's an error. If they exist but aren't scheduled for deletion, then return deleted as false. So this will be false, and there won't be any errors. But if they exist and are scheduled for deletion, then we'll return the deleted Boolean as true with no other errors. Okay, that's making sense to me. And then a note on how maps are passed into functions is that, like slices, maps are actually passed by reference. So even though this function, delete if necessary, does not return a map, if we mutate this user's map, it will be mutated for the caller of the function. So that's how we're able to delete something from the map, even though we're not returning the map once we're done with it. So the first thing we need to do is just check and see if the name that we're trying to delete exists. So let's do this. If blank okay colon equals users at name not okay. So this is that kind of special if statement syntax, right? Where we're actually ignoring the value itself. We're just interested in that Boolean value telling us whether or not this this key exists in the map. And if it does not, then we're going to go ahead and return the error not found. So false, because we always do 0 values for everything besides the error, and then errors.new not found. And we'll make sure to import that errors package. Okay, cool. And again, I'm just using this syntax here, right, to check if a key exists. Cool, moving on. Okay, so if we get past that guard clause to line 12, then we know that the user exists. So at this point, we need to check if they're scheduled for deletion. So I'm actually going to switch up my syntax here. The user struct has the scheduled for deletion Boolean. So I'm going to go ahead and do this on a separate line. And I will save that user. So I'll do existing user. And then we'll just do if not okay. So that down here, now I can use that existing user struct. So I can say if existing user dot scheduled for deletion. So if they exist and are scheduled for deletion, return deleted as true with no errors and delete their record from the map. So we need to use this built-in delete function. So we'll delete users name. And then we'll return true nil. All right, so if they are scheduled for deletion, we'll delete them and report back that we deleted them. Cool. Otherwise, if they're not scheduled for deletion, return deleted as false with no errors. So return false, nil. Okay, that looks right to me. Let's go ahead and run that. Attempting to delete John, deleted John. Attempting to delete Musk, not found. Santa, not found. Attempting to delete Cade, did not delete Cade. Okay, cool. So I mean, all that it looks like all the cases were covered. Let's just come down here and take a look. Okay, so we had a John, and John was deleted. And then attempting to delete Musk, there's not actually a Musk in the map, so not found makes sense. There's also not a Santa, and Cade was not scheduled for deletion, so he did not get deleted. And then the final map still has those keys. That looks correct to me. In this next section, we're going to be covering some of the material from the Go blog. Now, I'm not going to read all of this out. That would be a little dry, but I definitely recommend reading this over if you have the time. Otherwise, I'm going to cover kind of the key points. So the first question is, what makes a type qualify to be able to be used as a map key? Okay, so any type can be used as a map value, but not every type can be used as a map key. And that's because map keys may be of any type that is comparable. So things like strings, booleans, numbers, all of those can be compared for equality. What cannot be compared for equality are slices, maps, and functions. And kind of one of the reasons for that is slices and maps and functions, they're kind of just pointers to addresses in memory. So if you compare one slice to another slice, you're not really comparing the underlying values. You're actually comparing kind of where those two slices are stored in your computer's RAM. And because they're stored in different places, you'll actually get two slices with maybe the exact same values stored in them. Say slice 1 has the numbers 1, 2, 3 in the first 3 indexes, and the second slice has the same. They might still be compared as unequal because they're stored in different addresses in memory. So, I mean, all that being said, long story short, you just can't use slices and maps and functions as map keys. So, to answer the question, what makes a type qualify to be used as a map key? The type is comparable. This next question is interesting and kind of plays on the idea that we can nest maps kind of one inside the other, or we could do something that's arguably simpler. Let me show you what I mean. So here is an example of a map of strings that maps to another map, which maps from strings to integers. So like the first string kind of maps to the second string, which maps to an integer, if you want to think about it that way. If you're familiar with JSON objects, this would be like mapping JSON objects kind of down multiple levels of keys. So in the example given in the Go blog, essentially what's being said is we're mapping two strings to a count. And so what that looks like in code is if we want to get access to the count, we actually have to go to the map, index the nested map with a key, and then index into that next map with another key before we get the value out. Now, this looks simple on the surface, but what actually happens is when you go down those nested levels, you actually can't be sure that the inner map exists. And so to avoid panicking, your code will actually panic, by the way, if you try to access a key in a map that is nil. So to avoid panicking, you have to check and make sure that those nested maps actually exist, which just results in a lot of extra code. So while nesting maps definitely works, and I've used it quite a bit, there can, in some instances, be a simpler way, which is to actually use a struct as a key. Notice that a struct was not named as one of the non-comparable types. Structs are comparable. So if you want to create a map that kind of has multiple keys that kind of combine together to form a composite key, then just create a new struct, right, with two values inside of it, and those two values kind of unique together create their own key. So this simplifies a lot of things where now we can have one map and we can use that struct key to create kind of uniqueness across two different values. This might be useful, for example, if you're trying to create a map that's unique for first last name combinations, right? You want Lane Wagner stored in two different fields, first name and last name, to be unique together. So to answer the question, which is simpler, to use a struct directly as a key or to nest maps? And The authors of the Go blog, and I would agree, argue that using a struct directly is going to be simpler. Let's jump right into this next assignment. It says we have a slice of user IDs. Okay, so those are strings. And each instance of an ID in the slice indicates that a message was sent to that user. We need to count up how many times each user's ID appears in the slice to track how many messages they received. Implement the getCounts function. Okay, so that's this one. It should return a map of string to int so that each int is a count of how many times each string was found in the slice. Okay, cool. Simple enough. So let's create a new map. So this will be the counts map. And it's going to be a map of string to integer. And then let's loop over all of the user IDs. So for blank user ID in range user IDs. Okay, we're going to ignore the index because we don't care about it. And the first thing we're going to do is check to see if a value in the map for the given user ID already exists. So count, okay, colon equals user IDs, counts at user ID, right? Cool. In fact, now that I type that out, I'm not actually sure that I need this, because if I don't use this access will still work. It's just if the key didn't exist, count will be 0, which is fine. So actually, I don't even think I care. Cool. So we get the count. It'll be 0 if it didn't yet exist. And then we just increment it by 1. So count plus plus. And then we'll save it back into the map. So counts at user ID equals count. So we're just grabbing it out, incrementing it by 1, and putting it back. That seems like what we want to do, right? And then at the end, we'll just return counts. Cool. Let's go ahead and run that and see what we get. Generating counts for 10,000 user IDs. Counts from selected IDs. 00 has 31, FF has 27, DD has 37. Okay. And if I look down here, it looks like the IDs are being generated randomly. Cool. So let's go ahead and submit it because this feels right. Cool, we're good to go. This next section is about a piece or an excerpt from the Effective Go book. That is a book that I'd highly recommend reading. Some of the stuff's a bit outdated. They've made the decision not to continuously update Effective Go, but it is an open source book. You can go read the whole thing for free, and the link is right there. So go check that out if you're interested. That said, you don't need to. I'll be talking through the parts that we care about here. So maps can have, at most, blank values associated with the same key. The answers are 1, any number of, 3, and 2. Well, maps are associative, right? They map a single key to a single value, and you can't have duplicates of the same key in a map. That wouldn't make any sense, right? Then when you put in a key, you would maybe get back a slice. Like, that doesn't quite work. So the answer is maps can have, at most, 1 value associated with the same key. The next question says, attempting to get a value from a map where the key does not exist, returns the closest value, panics, or returns the 0 value. That's covered here in the section on missing keys, but basically to summarize, if you attempt to get we actually covered this in the last coding assignment, but if you attempt to access a key in a map where the key doesn't exist, you'll just get back the 0 value. So for example, if it's a map of strings to integers, and you access a string that doesn't exist, you'll get back as the value 0. And that's kind of nice just because accessing values in a map is a safe operation. Your code will not panic. So to answer the question, it returns the 0 value. And it's also worth pointing out really quickly that if the map doesn't exist, so not that the key that you're trying to access doesn't exist, but if the map itself doesn't exist, if it's a nil map, then your code will panic. So that is a dangerous operation. You want to make sure you're always accessing values in maps that have been initialized. The next question is, a function can mutate the values stored in a map and those changes blank the caller. Affect or do not affect the caller. Now, the answer to this one is in this first section, that maps like slices are references. So when we pass a map into a function, that function can change what's in the map, and those changes will be visible outside of the function. This is different from primitives, right? Strings, integers, booleans, those are all passed into functions by value. If you mutate them within a function, the caller of that function will not see those changes unless you return those values. But the same does not hold true for slices and maps. So to answer the question, a function can mutate the values stored in a map, and those changes, they do affect the caller. The next question says, what does the second return value from a retrieve operation in a map indicate? So let's take a look at this code example here. So we've got this time zone map where we're accessing the map at a given key, and it can return two values. The first value is the value associated with the key, and the second value is a Boolean. Right? We used this in the last coding assignment. So a Boolean that indicates whether the value at the key is a nil value. Nope, that's not accurate. A Boolean that indicates whether the key exists. That's the one. Let's practice with some nested maps. So like we talked about earlier, maps can contain other maps as their values, not as their keys, right? So let's jump into the assignment. It says, because Textio is a glorified customer database, right? I mean, we're sending SMS and email messages to a giant list of customers. We're basically just a big customer database. We have a lot of internal logic for sorting and dealing with customer names. Complete the getNameCounts function. It takes a slice of strings, names, and returns a nested map. So this is going to be very similar to the last assignment we did. But this time it's going to be a nested map where the first key is all the unique first characters of the names, and the second key is all of the names themselves. So this could be useful if for some reason we wanted to get access to all of the names that start with A very quickly. So to kind of visualize this, we've got this example. If the input names slice is this slice here, Billy, Billy, Bob, Joe, it would create the following nested map. So the first key is just a letter. The second key is the full name, and then the value is the number of times that name showed up in the original list. And then it's worth pointing out here that the return value is a map of runes to a map of strings and integers. In Go, we often just represent individual characters as runes rather than strings of length 1. It just gives us a little more kind of a surety in our type system. Okay, so let's start by creating a new top-level map. So we'll call it counts, and we'll make that full map. Now, it's important to understand, because this map contains maps inside of it, we will need to continuously initialize new maps. I'll show you what that looks like. So now let's just loop over all these names. So for, we don't care about the index, name, and range names. Okay, so we've got a name. The first thing we need to do is actually check and see if we already have a map associated with the first character of this name. So let's get that first character. Let's do if, we probably need to do some safety checking. So like if length of name, actually the easiest thing to do would just be if name is the empty string, then we'll continue. We don't care about blank names. They don't do anything for us, right? So we'll just skip them. Great. If it's not the empty string, then we can say first character is name at 0. Okay, so that gives us the rune at the first index in the name. And then what we can do is look up in our map. So counts at first character. We can see if the inner map exists. So if it does not exist, not okay. Let's just keep it simple. If it doesn't exist, we'll just initialize it. So if it does not exist, we'll say counts at first character equals, and we'll initialize the new inner map. So we just need a new map of string to integer at that first character key, right? Right. In fact, to be explicit, I'm going to ignore the inner map there. So by the time we get down here to line 18, we should be 100% certain that counts at first character contains an initialized map. So then we can just simply do counts at first character at name plus plus, right? Because we've made sure that the inner map exists, and if the name key doesn't exist, it will return a 0, which we can then increment and save back into the map. So that should work just fine. At the end, we can return counts. Cool. Hopefully that makes sense. And we've got some test cases down here. Matthew, George, Drew, Philip, Bryant, and then a big list. Okay, cool. Let's run it and see what happens. Whoops. Cannot use first char, variable of type byte, as rune value. Right. So when you index into a string, right? So name is a single string in Go, then it is a byte type. But we want a rune type. So I'm going to go ahead and cast it and run it again. Cool. Generating counts for 50 for the first 50 names. Count for M Matthew is 3. G George is 1. D Drew is 4. We don't have any panics, so these counts look totally plausible to me. Let's go ahead and submit it. It's time to talk about first class and higher order functions, which are just really kind of confusing, complex terms for a much simpler idea, which is functions as data. A programming language is said to support first class functions if it allows you to pass around functions just like you pass around any other variable, storing essentially an entire function as a value. And then a function that uses that first class function, so a function that accepts another function as a parameter or returns a function as a return value, is said to be called a higher order function. Let's take a look at a concrete example. Okay, so here we have two functions, add and multiply. These are very simple functions. You should be able to understand what they do just by looking at them for a second. But here we have kind of an interesting function. It's called aggregate, and it takes as input 3 integers, a, b, and c, and it takes as input an entire function, right? So it takes a function, and we're calling it here arithmetic. It's the 4th parameter to the aggregate function. And this function has a specific signature. This function, arithmetic, must take as its parameters 2 integers, right, and return an integer itself. And then the aggregate function just returns an integer. So what does the aggregate function do? Well, it calls the function it was given twice. First, it calls it once with a and b, and then it calls it again with the results of a and b and c. So, for example, if we call aggregate with the numbers 2, 3, 4, and the function add, then it will add all 3 of those numbers together, right? Which would, in this case, print 9. And then we can also use that same aggregate function with the same numbers, 2, 3, and 4, but this time pass in that multiply function. And here we'll get 24, right? Because we're multiplying all of the variables together instead of adding them. It's okay if this is a bit confusing, if this is the first time you've worked with functions as data. Take a second to really kind of stare at this code and figure out this crazy function signature. It's actually not that complex once you kind of get past the scary syntax, but don't feel bad if you have to pause the video and take a good look. Let's get our hands dirty with this assignment. It says Textio is launching a new email messaging product, Mailio. I guess SMS and email, right? Fix the compile time bug in the get formatted messages function. The function body is correct, but the function signature is not. Okay, so this formatter function here looks like it will be a problem. Let's go ahead and run the code and see what kind of an error we get. So this is a compile time error saying we have a syntax problem. And that makes sense because here we're basically saying, well, the formatter input is a function, but we're not saying what type of function it is. And that doesn't work because get formatted messages is going to use the formatter function. So it needs to know essentially what parameters it takes as input and what it's going to return, right? Kind of like the arithmetic function here takes 2 integers and returns an integer. We need to update this function signature to kind of inform the get formatted messages function what this formatter function actually does. So if we look at the code, because we know the function body is correct, it looks like formatter accepts a message as input, which is a string, and it's going to return whatever should be appended to this formatted messages slice, which is a string. So it looks like it takes one string as input and returns one string as output. That kind of makes sense for a formatter function. So we say it takes a string and it returns a string. Let's go ahead and run that and see what we get. Cool, at least it compiled. It says, thanks for getting back to me, which returned, thanks for getting back to me, kind regards. Okay, cool. So the add signature adds kind regards to the end, and add greeting, thanks for getting back to me, hello, thanks for getting back to me. Cool, let's go ahead and run that. Awesome. So this might seem like an exercise in complexity, right? Like, why do I need to pass around functions as data? That just seems to add a bunch of, well, needless complexity. And for the most part, you're right. You really should only use higher order and first class functions if you have a very good reason to do so. So the question is kind of, what are the good reasons to do so? Well, first class and higher order functions are very often used for, on the backend side of the stack, HTTP handlers, right? So if you have some front end code that needs to reach out to a backend server and get some data, those handlers are typically first class or higher order functions because we need some code, right, the handler function, to run like in the future. We don't want to call it now, right? We want to call it when something happens. In the UI world, kind of on the front end side of the stack, they're often used in on-click handlers, right? So I write a function and I don't necessarily call it when my program starts, but I call it when something interesting happens, like the user clicks a button, right? When a button click happens, I want to call, this function. And so typically in code, we can represent that with a higher order function. We say on click, do this, and then we kind of give it the name of a function to call. And then just to review the definitions very quickly, a first class function is a function that is kind of being passed around as data. And a higher order function is the function that's using that first class function, right? It's a function that accepts a function as input or returns it as one of its return values. So the question is, what is a higher order function? It is a function that takes another function as an argument or returns a function. But it's not a function that is first in the call stack or a function with superior logic. So the next question is, what is a first class function? It is a function that is treated like any other variable, right? It's a function that we're going to pass around as data to probably be called sometime in the future. Function currying is kind of like a special kind of higher order function. It's a function that accepts another function as input. We're kind of familiar with that idea, but that also returns a new function as its output. So it's kind of a way of like enhancing a function with new behavior. It's kind of a weird concept to think about abstractly, so let's jump into this example. Okay, so here we have a function called self-math, and self-math is the curried function. It takes a math function as input that accepts two integers and returns an integer, and it returns a new function that only takes a single integer as input and returns an integer. And then what it does, again, it returns a function, right, that takes a single integer as an input and returns an integer, and it calls the math function that it was given with the same input twice, right? So we're kind of mapping a function that accepts two different integers into a function that kind of forces both of those integers to be the same integer. So like, what does that do in practice? Well, basically we can use our self-math function to convert a multiply function into a square function, right? So multiply takes x and y and multiplies them together. This new square function that we created dynamically only takes a single value and multiplies it by itself, right? Same with the add function. We can kind of use the self-math function to convert it into a function that just doubles its input, right? So we square 5, we get 25, we double 5, and we get 10. So when would currying be used in the real world? To be honest, I don't use it very often. But in backend server land, I do sometimes use it for middleware functions. So a middleware function is a function that basically changes the HTTP handler of a backend server. And just as a spoiler, we will be covering this in the project at the end of this course. But it's for kind of injecting some additional logic into a function. So say we have an HTTP handler that accepts as input a user ID and returns an entire user object with, say their first name, their last name, that sort of thing. A middleware function might do something like require an authentication token, right? So we can write all of our HTTP handlers that serve different data sort of independently, and then we can use a curried function to kind of require authentication logic on all of our HTTP handlers. In fact, in Go, currying is very often used to handle this sort of middleware problem. Now, if all of that went straight over your head, again, that's okay. It's kind of hard to talk about something that we're not working on at the moment. So again, we're going to cover middleware and HTTP handlers in the project at the end of this course. So stick around for that. So jumping into the assignment, it says the Mailio API needs a very robust error logging system so we can see when things are going awry in the back end. We need a function that can create a custom logger, a function that prints to the console, given a specific formatter. Okay, cool. So this function, getLogger, should return a logger, which is a function, right? It's a function that takes two strings as input and apparently prints them because it doesn't return anything. Right? And getLogger takes as input a formatter, which accepts two strings as input and returns a single string. Okay, so it says complete the getLogger function. It should return a new function. The inputs should be passed into the formatter function, the order they're given to the logger function. Okay, so let's start writing this. So we're going to return a function that takes two strings as input, right? And I'm going to reference up here for the syntax we're interested in. So I'm going to do A string, B string, right? And this function should return nothing. So we can just go straight into the body. And it says this function prints the formatted inputs. So formatter returns a single string. So we can just do fmt.println. And we're going to need to, oh, we already have fmt imported. Perfect. So we need to print the result of the formatter functions. It's going to be formatter, and we'll pass into the formatter A and B. Right, so we're returning a new function, a logger, that accepts two inputs, formats them, given the formatter that we were given, right? And then just prints it to the console. Cool, let's go ahead and run that. Error on database server, out of memory. Error on database server, CPU is pegged. This all looks good. Let's see how the test suite actually works. It looks like these are the formatters, colon delimit and comma delimit. And if you take a look at our messages, some are delimited by a colon, some are delimited by a comma. So that's how that is working. Very cool. All right, I'm going to go ahead and submit that. I think this is correct. Time to talk about the defer keyword. This is a really kind of unique thing to Go. If you're familiar with any other programming languages, it's unlikely that you're familiar with something similar to the defer keyword. At least I've never used it or used a concept that is similar to the defer keyword in another language. Fairly Go specific. Okay, so the defer keyword allows us to execute some function at the end of the current function, or when the current function exits. The defer keyword is very often used as sort of a cleanup step. For example, in this function here, copy file, we open a source file from the file system, and then we defer closing the file, right? So every time you open access to a file in the file system, you need to remember to close that file. Otherwise, you're sort of wasting computer resources. The problem is closing the file at the end of the function is a little tedious because we have multiple return statements here. So we'd kind of have to close it before both of them, if that makes sense. By using the defer keyword, we can just tell the Go programming language, hey, I want to call source.close right before the copy file function ends, and just defers it kind of until the end, and it will only call it once, no matter where the function actually returns from. On to the assignment. It says there is a bug in the log and delete function. Fix it. Let me expand this a little bit so we can see it. This function should always delete the user from the users map. Okay, cool. So we're given a users map, we're given a name, and we know that maps are passed by reference. So if we delete a map, it will be deleted in the caller's code as well. It should return a log string that indicates to the caller some information about the user's deletion. Okay, so delete should always happen, and then the kind of the appropriate log message should be returned from the function. That makes sense. But it looks like there's a bug. Okay, so let's go ahead and run the code and see what we get. So initial users, Brianna, Elon, John, Cade. Attempting to delete John, deleting Santa, deleting Cade. Okay, so John's still there. The problem is that we're trying to delete John, but John's not actually getting deleted, right? So we need to fix that bug. And if we take a look, John is an admin. And here we're returning log admin, but we're not deleting admins. So that's the real problem, right? The users should always be deleted. Now, here's the problem. We can do this. This will work. If I run this, my guess is this should fix the bug. Yep, John is no longer there. He was deleted successfully. But this is kind of gross, right? We're calling delete 3 different times. What if in the future we add another case and we forget to add the delete again? We'll have another bug. Well, what we could do is just delete at the top once, right? But the problem is if we do that, we delete the user from the users map too soon. And now this OK variable that's checking for existence so it can change which log is returned, like that logic won't work. It will just always be not OK. So we'll always just return log not found. So that's a problem. What we can do is defer the deletion. So this code says we'll call this delete function right before log and delete returns. So it's almost like the equivalent of adding this at every step of the way. So let's go ahead and run that, make sure it works. John's there, John's gone, perfect, and we have different logs getting returned. So that looks good. I'm going to go ahead and submit that. This chapter is not called Advanced Functions for no reason. Let's talk about closures. Closures are I don't want to intimidate you and say they're really hard, but they're a little weird. So let's take a second to understand how they work. Okay, a closure is a function that references variables from outside its own function body. The function may access and assign to the referenced variables. So in this example, the concatter function returns a function that has a reference to the enclosed doc value. Okay, so concatter is a function. It returns a new function, right? And that's what's happening here. And it's enclosing this doc string within the function. So it's getting initialized outside of the function and then getting used within the function. And what happens is basically when we call concatter to make this new concat function, we're saving a reference to this doc variable. So every kind of every subsequent call to this function that is returned, we'll keep adding on, right? Plus equals word. We'll keep adding on to the same doc variable. So let's look at what that kind of looks like in usage. So we're calling concatter and we're getting back this Harry Potter aggregator, right? That's what we're assigning this function. We're assigning this function into this variable. So Harry Potter aggregator is a function, right? It's specifically, it's this function right here. Cool. And then we're going to call it with Mr. And then we'll call it again with and Mrs. Dursley, right? We're calling it over and over and over. And what's happening under the hood is we're appending those words, Mr. and Mrs., onto that doc variable. So at the end, when we finally print what's being returned, which is the doc variable itself, we get the full sentence. Mr. and Mrs. Dursley of number 4 privet drive. Now, closures are one of those advanced things that you, to be honest, again, don't usually use in production code, maybe every once in a while, but they're very important to understand because it is very common to have kind of bugs surrounding closures. So if you don't understand what's going on under the hood, it can be really hard to debug kind of complex code that might even be using closures by accident. So the assignment says, keeping track of how many emails we send is mission critical at Mailio. Complete the adder function. It should return a function that adds its input, an integer, to an enclosed sum value, and then returns the new sum. In other words, it keeps a running total of the sum variable within a closure. Okay, cool. So it's going to be very similar to this, right? So we'll start by creating a sum value. So sum : equals 0, right? We're working with integers, not floats. And then we need to return a function with the signature. So return func x int returns an int. Oh, not returns an x, returns an int. And then here we need to add x to sum, right? So sum plus equals x. And then we need to return the new sum, right? And then if we go take a look at this test case, let's see. Okay, so we're adding these email bills with a bunch of different numbers. The test iterates over the bills. Okay, so we're creating two adders here. So we're creating a count adder and a cost adder. And then let me expand this. I'm gonna just make that basically full screen. So the test actually creates two different adders, two different instances of our adder function. Right? And one of them is going to count how many bills there are, and the other one will keep a running total of the cost of all of the bills, right? So we're actually using our function twice for two different things, and they'll each have their own enclosed sum count that they keep track of differently, right? The count will have its own, the cost will have its own. The count is simple. It just adds one every time. The cost will add the actual cost in pennies. Cool, let's go ahead and run this. So, and these values are getting interpolated into this message. So you've sent one email, costs 45 cents, two emails, 77 cents, three emails, 120 cents. It's like all of these are going up. That makes sense. I mean, we could even go verify, right? 45 plus 32, 77. That looks right to me. Let's go ahead and submit it. All right, we're on to a little quiz about closures. Can a closure mutate a variable outside of its body? Yes, that's basically the entire point of a closure. Another little review question here. It says, when a variable is enclosed in a closure, the enclosing function has access to blank, a copy of the value or a mutable reference to the original value. Well, if it was a copy, then our sum never would have worked, right? Because we'd be working with a new copy of the sum variable every time. So it's actually a mutable reference to the original value. We've already been using anonymous functions kind of all throughout this chapter. Now let's kind of just talk about what they are. So anonymous functions are exactly what they sound like. They're just functions that do not have a name. They have no name. Anonymous functions are really useful when you're kind of just one-off, maybe creating a closure, you're returning a new type of function. If you're not defining the function for like use across the entire program, but you're more using it as a value, using it as a first-class function, that's when you're going to see anonymous functions used the most. So as an example, here we have an anonymous function declaration, right? We're creating a new function, we're defining its internal logic, its function body, but we're not giving it a name, right? There's no name for this function that we're passing into do math. It is an anonymous function. The assignment says, complete the print reports function. Call print cost report once for each message. Okay, let's take a look. Print cost report looks like it takes as input a function, cost calculator. Great, okay. Call print cost report once for each message, pass an anonymous function as the cost calculator that returns an int equal to twice the length of the input message. Okay, let's go ahead and do that. So, it says to do it once for each message, yeah. So for message, range messages, call print cost report, and print cost report takes a cost calculator, which is a function that takes a string and returns an int. It's said to use an anonymous function, right? So funcs, we need to actually define our x, string int. We need to define the body that returns an int equal to twice the length of the input message. So x is a string. In fact, I'm going to name this message. And we'll return the length of message times 2. Right? Twice the length of the input message. And then print cost report takes a second parameter, which is the message itself. Right? I think. Am I reading this correctly? Cost report takes the calculator and the message itself. Yep, because it's then going to call the cost calculator and then print kind of a little report. Okay, cool. That's looking pretty good to me. We don't return anything from print reports. Okay, let's go ahead and run this. So message, here's Johnny, costs 28 cents. Go ahead, make my day, 42 cents. You had me at hello, 38 cents. That's looking correct, right? There's 19, 28, not 19. What's half of 28? 14 characters there. Looks good to me. Okay, let's go ahead and submit that. Let's talk about pointers. And in order to understand pointers, we need to talk a little bit about RAM, or memory, right? Random access memory, which is basically the part of the hardware in our computer that stores data, right? Because pointers and variables are all about kind of how we store data in the memory of our computer. Let's start with something simple. Let's create a new variable in our program, and let's call it x. And we'll set x equal to 5. Under the hood, what happens automatically when we create a new variable and set it equal to 5 is somewhere in our computer's memory, that variable's value is going to get stored. So let's say, for the sake of the example, that it's stored here in memory address 169. Now, memory in your computer, you can think of it as fairly simply a memory address that stores a value. So we've got kind of, millions of different memory addresses in which we can store data, and somewhere in memory, that value needs to live. So let's just say it gets assigned, again, automatically to address 169. Great. Now, what happens if I create a new variable, let's call it y, and set it equal to the current value of x? Y actually gets a new copy of the value. So x lives here at address 169. Y, let's just say, is going to live at address 170, and we get a copy of that 5. So down here in this table, this is where we're going to keep track of all of our variables. We'll say that x, so x is the variable name, lives at address 169, and it stores the value 5. Now y lives at address 170 and stores also the value 5. At its most basic, a pointer is just a variable that stores a memory address. So let's say, for example, that we create a new variable called z, and we set it to point, which uses the ampersand. I can't draw an ampersand. Pretend that that's an ampersand. A reference to x, right? It points to x. What that does is that we're creating a new variable called z. It's going to get a new address. Anytime we create a new variable, it's going to live in a new address in memory. Let's say it lives at address 171. But its value, instead of being 5, instead of being a copy of x, because we used kind of the pointer syntax or the reference syntax, the value is going to be the address of x. So we're going to store 169, which is the address of x, as the value. And z is going to be a pointer type. So kind of the way the Go programming language works is it knows that z is effectively pointing to the value 5, right? Because its address is 171, which stores a pointer to 169. So we can look up the value 5 at address 169. So what this means is if we update the value that z points to, under the hood, we're updating x. So we can do things like pass pointers into functions, change the underlying value, and the value outside of that function is also changed, which again, in a language like Go doesn't happen normally, because typically if you pass a variable like x into a function and then change it, those changes are not seen outside of the function. You would need to return the updated value and then assign it into a new variable. So pointers basically allow us to change the value of something from within a function, right? From within a different scope. Let me show you what that looks like in a quick example. So remember that z stores the value 169, which points to this address, which stores the value 5. So if we want to update the value of x without having access to the original variable x, what we can do is use the dereference operator, which is an asterisk. We can dereference z. Now this dereference operator essentially follows this chain and finds the value, right? And we reassign into it, let's say the value 6. So this becomes 6, and this location in memory is updated now to hold the value 6. So we've updated the value of x without even using, right, the name x. So now that we've kind of covered what a pointer is, let's look at just a little bit more of the syntax in code. So the type of a pointer is not the type of the underlying value alone. So if I want a pointer to an integer, I actually have to use this syntax here. I'm creating a new variable called p, and it's being initialized as a pointer to an integer. So a pointer is a specific type in Go. Now, to be fair, it's not super common that you're creating blank pointers, and the 0 value for a pointer is nil. More often than not, what you're going to do is have a concrete value like this my string hello, and then you'll create a pointer to that value by using the ampersand like we talked about. So in this case, the type of my string is string, and the type of my string pointer is a pointer to a string, which would be syntactically star string. There are kind of two primary reasons that you would use a pointer in the Go programming language. The first is the more common reason, which is you want to be able to pass a value into a function and change the value and have those changes kind of persist outside of the function, right? Because normally when you pass a value into a function, a copy is passed in. So if you want to pass in sort of the original value so it can be changed and updated, you might use a pointer. The second reason is if you're very concerned about the performance of your program. Every time you create a copy of a variable in memory, you have to copy that variable in memory, right? Which takes some time. So if you're dealing with lots and lots of data and you're trying to be very performant, you can make micro optimizations and kind of use pointers under the hood if you want to avoid all of that memory copying. Now, I will say that you usually won't want to do this up front because pointers are dangerous and they can lead to bugs if not used properly. So generally speaking, I would recommend against making those performance optimizations unless you really need them. Let's jump into the assignment. It says fix the bug in the send message function. It's supposed to print a nicely formatted message to the console containing an SMS's recipient and message body. However, it's not working as expected. Okay, so let's run the code. And we get these kind of weird looking values that are getting printed here in the to and the message fields. Now, this is hexadecimal. It's not binary, it's not decimal, it's hexadecimal. And this is the default formatting for a memory address. So we have these ampersands here. They're creating pointers to the underlying values. That's not what we want. It's not what we want here, right? That's why this looks disgusting. We need to dereference, or sorry, we need to remove the reference. So I guess dereference. We need to remove the ampersand so that we are no longer creating pointers. So run it again, and we get the values themselves, which is what we've been asked to do. Let's recap some syntax. Sometimes it can get a little confusing between the asterisk and the ampersand, what each of them mean and in what context. So when we're talking about the type of a variable in Go, a pointer's type is star and then, the type of the underlying value. So a pointer to an int is star int. An ampersand is used to reference a value. So if we want to create a pointer to the myString variable or the myString value, then we use an ampersand. So the ampersand followed by the name of a variable creates a pointer to that variable. Now here's where it can get just a little bit tricky. The asterisk is again used to dereference a pointer. So the asterisk is used in a pointer's type. It's also used as an operator to dereference a pointer. So when we say asterisk myString pointer, this refers to the underlying value. So we can actually change the underlying value, say by assigning it to, in this case, a new string. So in short, ampersands to create new references or new pointers to a value, and the asterisk is used to dereference a pointer and get back at that underlying value. Let's hop into the assignment. It says complete the remove profanity function. It should use the strings.replaceAll function. So this is a built-in function in the standard library in the strings package to replace all instances of the following words in the input message with asterisks. It should mutate the value in the pointer and return nothing. Do not alter the function signature. Okay, cool. So remove profanity takes as input a message variable, which is a pointer to a string. So because it's a pointer, we're going to be able to mutate it without returning anything explicitly. Okay, let's jump into it. So first thing we're going to do is dereference the message pointer and store its value in a new variable called message value. And then we'll just update this by using that strings.replaceAll function. So strings.replaceAll. We want to replace the values in message value. We want to, or I should say, we want to replace substrings from message value. We'll look for the word dang, and we'll replace it with 4 asterisks. And we want to do the same thing twice more with shoot, which has 5 letters. So let's add an asterisk, and heck, which has 4. So that should be good. Cool. Let's run this. I need to import the strings package before I forget and see what happens. So in its current state, we actually did not update anything, right? Shoot is still there. Dang is still there. That's because we actually need to point the message pointer to a string back at the updated value. So we can do dereferenced message equals message value. Let's run that. Perfect. Let's submit it. Now we've got a pointer quiz. So the question is,